In my previous video I was giving some background as to how I got into electronics, and I showed this device. This is something I built many years ago. I started building it when I was about 12 years old. It took me 6 months or so to build, so probably finished it when I was 13. Made a few modifications to it a few years later. But it's generated quite a bit of interest, and I've been asked to give a bit more information on it and just briefly explain how it works. So I thought I'd do that in this video. Just bear in mind as I go through this that I was very young when I designed this, so it's not necessarily a particularly good design, but I was learning as I went. And it was an interesting project, and I did many such projects. I've got many pieces of equipment that look like this. I used to buy these cases. You've probably seen them. They're not very expensive. I didn't have a lot of money, so almost all the parts are reclaimed, except the case. I think the case is probably the only part I actually bought, and then you just cut out the panels to suit. Didn't have any power tools. Everything was done with a small hand drill and files, and didn't have PCB drills, didn't have a CAD system. This is before the internet existed, so even things such as data sheets were hard to get hold of for the parts. So it was a real steep learning curve for me to do this. I had been playing with electronics even then for quite a few years, so this is something I did out of interest. But I thought I'd just show you some of the circuits that are in here, and then you can either have a good laugh or you might find it interesting. So I'll take the top off again. So inside, in case you notice this and wonder why it's here, some of these are to hold the boards in place, but the cork deadening is because there's an internal microphone in this, and it was an audio spectrum analyzer, so I didn't want the hum from the transformers getting into the microphone, so this is just for sound deadening. So before we start pulling the boards out, I thought I'd just show you through the schematics. So as I went, I was also learning how to draw schematics, trying to figure out how to design electronics. So it was, as I say, quite a steep learning curve. So I'll just briefly go through the various circuits and explain how they work. Not the best way to design this sort of thing. In fact, I built another one of these, a similar sort of machine, about 8 years later, based around a Z80, and had about 1/10 of the electronics in it. But when you do everything discreetly like this, then obviously it gets fairly complicated. So what we have here, this is the clock generator, and it's all digital. There's no analog controls on this. So when I wanted to set the scan speed or clock, what I wanted to do was be able to set it through a series of push buttons, and that means I needed some way to generate a clock based on some digital values. So this is quite straightforward. It's just a series of 4-bit magnitude comparators. If you're not familiar with these devices, it just takes 2 4-bit inputs, and the output is high or low based on whether input A is larger or smaller than input B. And so you can use this to generate an output based on the magnitude of a digital value, which is what it does. So this is just really a 12-bit clock, and the 3 groups of 4 bits are used to control the point at which the output is effectively daisy chained into the next, and so you can generate a cascaded counter. And then the other 4 bits used for the comparison are generated down here, and the 4 bits are also then used to control some 7 segment displays, and that's what this is. It's just a 7-segment display that shows the current setting for the clock generator. And then we have it has to be gated, of course, because it's also a pulse analyzer, so I needed to be able to gate the clock. So there's some controls down here, and also we have some settings to allow different scales to be selected, so we can have different orders of magnitude for the frequency it runs at. And then we have a switch down here that determines what range we're in. So it's fairly straightforward, and the clock just comes out here, gated of course. But this was kind of an interesting project in its own right. Allowed me to generate a wide band or wide range of frequencies with a digital output displayed, and this was the heart of the system, in as much as it generated the main clock that drove everything else. Later date I added the battery. I put that on a separate board in case it leaked. I didn't want it damaging the rest of the units. As it turned out, it was quite a good idea because it ultimately has leaked. I didn't really expect at the time to still have this many decades later. But this is just the basic layout. Like I said, I didn't have a CAD system at the time, and even most of this paper was reclaimed, so if you see weird things on the back of some of the sheets, then just ignore it. It's just that I was reusing paper. So we have within the unit a digital memory board and a set of 19 bandpass filters, and to select the bandpass filter that's required there was a multiplexer, and this is the design for the multiplexer. So as I say, there was actually 20 channels. Channel 20 was a clamping channel. It clamped the input to 0 volts to allow the A to D converter to be calibrated. As I said, there wasn't the internet at the time. I didn't have any data books for the devices I was using, so I borrowed data sheets or somehow found the data for various devices, and I had to draw it out on a separate sheet so that I could make use of this information and know which pin was which on each device. These days you just go on the internet and Google the part number and get the data sheet, but back then much more difficult to do that. Next circuit was the memory board. This is really the one I started the project for. In fact, when I originally started this, I wasn't going to build the instrument. I was just really going to make this board up. And in fact, this isn't the board I started with. I started with a much older type of memory device. Unfortunately, I can't find that board. That's why you'll notice when we took the boards out that this memory board is much newer material than the others. I think it was about 2 years later when I replaced the original board with this one. Pretty much identical. The only thing that was different was some of the control sense in terms of their whether they were positive control or negative, high or low, were different, and that was the only real change on the board. The rest of it was identical. But what we have here is the memory chip, and there are two modes it works in, either acquisition or display, and it could do both at the same time. So when it was acquiring data, we have an incoming clock. This is the clock that comes from this digital clock circuit, and it's used to drive a pair of counters that gives us an 8-bit binary value. Counts up, that selects the address for memory, and then as it selects each of the addresses, the data on in that location is put onto the data bus. We've got some memory select lines to allow us multiple memory banks, and they're controlled through the memory bank circuit, which we'll look at later on. When the data comes out, then it comes down to this D2A circuit through some latches. The latches are updated and the control of the rest of the system. It needs to be gated, of course. That goes through an amplifier and out to the circuit that controls the display. This lower portion, which takes the same count that's driving the address for the memory, is used to control a second D2A, and that D2A is used to generate a ramp that is used to control the sweep of the electron beam across the display. And doing it this way meant everything's synchronized. So the same count that was selecting the memory location was also generating the sweep for the display, and it meant everything was nicely synchronized, and I didn't have to worry about synchronizing the two independently. That worked very well. It could acquire data, it could do both at the same time, so while it was acquiring data it could also transparently display the data at the same time, or it could just select one of the memory banks without any acquisition coming in and display that independently. Okay, so the next circuit, and when I was designing the boards, as I said, I didn't have a CAD system, So what I used to have to do is draw it all out with pen and paper, or pencil and paper, figure out how I was going to lay it all out, and then when I came to actually make the boards, I used the kind of rub-on transfers that you used to be able to get and or etch-resist pen. I'd spend several evenings laying out the board. Bear in mind that this is the underside of the board, so when I was designing it from the top down, but when you come to lay out the board it is of course mirrored, so you have to remember that when you're doing the board layout. To drill the boards, I didn't have a PCB drill, so I'd use a small version of one of these jeweler's screwdrivers, rest it on the board, spin it round till it went through the board, and then go on to the next one, and ended up with mini blisters for months on end while I was doing this. But that's the only way I could do it. I didn't have a PCB drill. So it would take probably 2 or 3 days to do one of the board layouts once I'd designed it. Okay, the next circuit is the signal processing circuit. This was fairly complicated and probably took the most time to design within the project. So there were various input channels that could be used, and I could set the gain of the input, so it would take signals from 10 millivolts per division up to 10 volts per division, and that's where this was controlled. It was a buffer and a series of analog switches that set the gain of the amplifier. And we also had things such as logarithmic amplifiers, so it would work in either logarithmic mode or in linear mode, depending on what I wanted to look at. And then it had various other things such as noise generators, different gains, separate channels for 2 different signals, so I could compare signals. It was quite a capable unit, and these were things that I kind of added on at later dates. It also had the ability to display the data either as a line or as a bar graph, and to generate the bar graph we have a voltage controlled amplifier, so the incoming signal that would normally be displayed as a line was fed through the voltage controlled amplifier, and this used a built-in oscillator to generate an envelope that was the profile of the line, so it could show the data in a bar graph form. I say all very complicated, way over complex, but as I said, I was learning this as I was going, so I didn't have an overall design for this when I started. I was just learning as I went. One thing I did learn early on was to document things, so I was writing down how to set up these boards and test them as I went, and excuse the handwriting. Remember, I was quite young when I did this, but ended up with quite a good comprehensive setup and test procedure. Figuring out how to lay out the various parts of the system, and then plotting the individual profiles for each of the 19 filters. In fact, I plotted these in quite some detail, if I can find the relevant part. So I was plotting the filter profile for each individual filter to determine the values for the capacitors and the resistors. They were third order filters, bandpass filters. And this is one of the design challenges, was to get all these into the space I had on the board, which we'll have a look at the board in a few minutes. But made sure they were all the correct profile, and did that for each of these separate filters. Some of the boards are double-sided, and if you've ever made boards like this at home, you know that's quite tricky, and that was something that I had to spend a bit of time figuring out how to do to get the 2 sides to properly line up. And as I said, it took quite a long time to do the individual boards, and because I had 19 circuits that were identical to put onto a single board, I ended up making a small template that I could sellotape to the board, and then I actually drilled through the holes using the little screwdriver, and then I used the holes to line up the pads, and did it that way rather than laying out the pads and then drilling the holes later. Did the layout, so again, excuse the layout, this is just the way I did it at the time, and again I was learning the ways to do this sort of thing, designing the profile I wanted for the filter, the various layouts, how each circuit was going to work, the various timing for each circuit. These aren't the initial drawings I did. These were kind of cleaned up versions. There were obviously quite a few different steps I went through to get this far. One thing I learnt, which I later learnt is done in most vintage computer monitors, was to synchronize the sweep of the display with the incoming mains. If you're familiar with vintage computers, you know that most monitors do that anyway. I didn't know that at the time, and if you don't do that, you get kind of slow wavering of the display. So even though the refresh rate was meant to be 50 Hertz on the display, it wasn't exactly 50 Hertz, so it did tend to cause the display to breathe, so in and out or up and down. But I found that locking that and synchronizing it to the mains frequency stabilized it, so although there's still distortion, you can't see it because it's fixed. And that's how this circuit worked. Again, setup for the individual boards, the pinout locations for each board, so this would be equivalent to a Gerber file layer these days. We have the voltage controlled amplifier. This is the one, as I said, that generated the profile for the bar graph display. So when you're selecting the various setup on the keys, you've got this key, it says line or bar, and that's selected either straight through from this circuit or engage this circuit. Log amplifiers, we've got log and lin, and that again either pass the signal directly through or engage the logarithmic amplifier to put the device into log mode. Again, more board layouts, and that's pretty much it. The rest is control electronics. It was the various switch controls that are just latches, or the board layout. So it's a double-sided board, and I had to design both sides and figure out how to actually make them. The individual circuits, so these are what we've already looked at, but in a bit more detail. So when I was designing it, what I tended to do was design each part separately, test it, and then draw it into the final schematic. And when I had what I thought was a complete schematic for a given board, I would make the board, test it, and then if it worked, I would start wiring it into the instrument. Memory control board is the interface between the memory control itself and the rest of the electronics, and this just takes the incoming clock signals or control signals and generates quite a few different signals out to control the various parts of the system. So whether we are selecting different settings on the key panel, or if it's part of the automated system for, in this case, this particular part is the synchronization of the display with the mains frequency. This all has to be controlled, and that was on a separate board. The bit I found hardest designing this was this part of the circuit. Now the CRT came out of a small television that started appearing about that time, and I was lucky enough to find a faulty one, which was lucky because they were very expensive at the time. The small 6-inch TV, very expensive back then, very long tube, but what I had to do was figure out how to generate the high voltages it required, but the hardest part was figuring out how to scan it. It's magnetic deflection, so requires some very high peak currents to drive it that are not the same profile as the scan that you want, because you're feeding into a highly inductive load. So this took quite a long time to develop, and although it looks quite simple, it took me probably a good 2 weeks to design and get this working properly. There were two of these, of course, one for the X and one for the Y. There are slight differences because they work at very different frequencies, but fundamentally the circuits are the same. Power supply was fairly complicated. We needed an isolated supply for the CRT heater, and this is a 1.2 volt heater on this particular tube, and 12,000 volts for the EHT, and we needed 400 volts for the BIOS, 500 volts for the second BIOS, and we needed about 350 volts for the focus, plus or minus 15 volts for the signal circuits, plus or minus 15 volts for the scan circuits and a high current 5 volt supply for the electronics. These are all the values for the various filters, and these are what gave the profiles that are required for the 19 filters for the spectrum analyzer display. This is the circuit for the CRT supply, so it generates the EHT and the high voltages for the bias and the focus for the CRT. This is the white noise generator, the broadband white noise that was used to enable me to do analytical testing. So when we're looking at the spectrum for noise, if it was, for example, looking at the spectrum within a room, then we'd feed white noise into the amplifier and speaker system, and then we could pick up the resulting signal coming back. And so the way this worked overall, it generated wideband white noise that wasn't flat, and then it kind of cut it down and looked at just the lower portion of it, so it gave us a flat response. And that worked quite well. It gave us very good results. And again, the rest of this is really just the kind of design phase and notes and whatever else, how to make various parts work. And it's very time consuming. I spent pretty much every night for 6 or 8 months doing this, and ended up with this instrument that didn't really see a lot much use, to be honest. I used it maybe 20 or 30 times, but it was mainly the building of it that I was interested in rather than the final use of it. So I'll pull a couple of the boards out so you can see the sorts of results you can get or could get back then with minimal tools. So a couple of ground straps at the top just to help minimize the noise I was getting. And this is the filter board. So this is the 19 filters and multiplexer. So as you can see, there's quite a lot packed onto this board, and this is one of the design challenges I had at the time, was how to get everything fitted onto a board of this size. Bear in mind I was making this at home with almost no tools at all, and worked extremely well. It gave me very good results. Getting it all on here was a major challenge, but ultimately worked very well. So we then have the analog board. So this is one of the more complex parts in terms of the design of the system. Let's get this board out of the way first. So the blue connectors go through to the display. But otherwise relatively straightforward. Obviously works fairly well. And then we have the analog board. So this is the board that does all the analog amplifiers, log amplifier, etc. Got some ground plane on here. This is the input amplifier, so I needed to use a ground plane. But one of the design challenges here was getting all the pots along the top so they were accessible. Obviously the boards are quite densely packed in here, so if I'd put the pots any further down, it would have been hard to get to them. This is quite old now. It's probably best part of 40 years old, maybe a bit older. So as you can see, there is some corrosion starting up, and it doesn't work anymore. I want to do some fault finding on it, see if we can get it working. But it gives you some idea what you can do with absolute minimal tools. I won't tear the rest out. All we've got now is the control board for the digital circuit. We'll pull this board out. We've got the power supply board. So this is the board that generates all the power rails. Again, you can see it's kind of a bodged at-home type of construction, but it was really trying to fit it all into the space, bearing in mind that I could only use components I could find. And then at the back, tucked down here, we've got the scan circuit. This is what's responsible for the magnetic scan of the CRT. and then at the back here we've got all the transformers for the various supplies. So that's it for this video. If you do want to see this working, or you want me to repair it, then let me know. And if you want any more information about it, then again leave a comment.